What if a particle on the far side of the universe is mysteriously connected to a particle in your hand? The moment you measure one, the other's measurement result is determined. Distance doesn't matter. Einstein called this spooky action at a distance and rejected it. He believed quantum mechanics was incomplete, but experiments showed that the local realism Einstein valued is difficult to uphold. What does quantum entanglement teach us about the nature of reality itself? And why couldn't even a genius like Einstein accept this? Today, let's explore quantum entanglement, this strangest phenomenon in the cosmos. By the time you finish this video, the concept of reality you thought you understood will be fundamentally shaken. Chapter 1: Einstein's Challenge. 1927. Physicists from around the world gathered in Brussels. There, Einstein and Niels Bohr clashed intensely over the essence of quantum mechanics. According to quantum mechanics, particles exist in a superposition of all possibilities until observed. Like Schrödinger's cat, Einstein couldn't accept this. God does not play dice. This was Einstein's conviction. He believed quantum mechanics was incomplete. He thought there must be hidden variables that, if known, would explain everything deterministically. And in 1935, Einstein published a decisive paper with Podolsky and Rosen in Physical Review. The EPR paradox. If two particles are in an entangled state and you measure one, you can predict the measurement result of the other. Distance is irrelevant. And here's where a crucial question emerges. What EPR questioned was whether this correlation could be explained by local reality. If the particle's properties were determined before measurement and there's no faster-than-light influence, then quantum mechanics must be incomplete. This was Einstein's argument. This was the greatest challenge to quantum mechanics. But physicists would find a way to settle this debate. So let's see how scientists solved this mystery. Chapter 2: Bell's Inequality and the Triumph of Experiment. 1964. John Bell, a physicist from Northern Ireland, found a way to settle this debate. He showed that local hidden variable theory cannot reproduce quantum mechanics predictions. This is Bell's theorem, and he derived an inequality that could be used to test it. Local realism is the idea that physical properties are determined before measurement, and that influences on distant locations don't exceed light speed. This aligns with our intuition. But quantum mechanics makes different predictions. 1972. John Clauser performed the first decisive experiment. He tested Bell's inequality in the form known as the CHSH inequality. The result was unambiguous. The inequality was violated. Local hidden variable theory was strongly constrained, but skeptics pointed out loopholes. So in the 1980s, Alain Aspect conducted more rigorous experiments. He randomly changed the measurement settings after the particles had separated. Still, the correlation remained. And in 2015, multiple research groups, including Ronald Hansen's team at Delft University of Technology, succeeded in closing major loopholes like detection efficiency and locality simultaneously. Quantum entanglement is real. This is now beyond doubt. Think about that for a moment. Bell experiments showed that the framework of explaining reality with local hidden variables is difficult to maintain. Whether to abandon locality or pre-measurement determinacy depends on interpretation. But the reality our intuition teaches us has been fundamentally called into question. In 2022, Clauser, Aspect, and Anton Zeilinger received the Nobel Prize in Physics for their contributions to the experimental proof of quantum entanglement. So what does this discovery teach us? Let's explore the deeper meaning. Chapter 3: Information and the Nature of Reality. Here's what many people wonder. If quantum entanglement creates instantaneous correlation, why can't we send information faster than light? The answer lies in the essence of quantum entanglement. When you measure one particle, the result is random. And when you measure the other, it's perfectly correlated. But you can't control the first measurement result, which means it's impossible to send an intentional message. What relativity forbids is, quote, faster than light signals. Quantum correlation is not a signal. There's a technology called quantum teleportation, a technology that transfers quantum states to distant locations. But this also requires classical communication to convey Bell measurement results. That communication is limited to below light speed. Causality is not violated. Yet quantum entanglement is revolutionary. Quantum computers use quantum-specific properties like entanglement and interference, potentially surpassing classical computation for certain problems. However, major challenges like error correction remain for practical implementation. Quantum cryptography enables the ultimate security that's in principle impossible to eavesdrop on, thanks to the laws of physics. Though countermeasures against attacks exploiting implementation imperfections are essential. More recently, research on quantum networks that deliver entanglement over long distances has accelerated. The key is quantum repeaters, which attempt to extend loss-sensitive entanglement in stages through quantum memory and relay. And here's where an astonishing hypothesis emerges: the theory that quantum entanglement itself generates space and time. This is the ER equals EPR conjecture. The stunning proposal that quantum entanglement, EPR, and wormholes, ER, are actually equivalent. In 2022, an experiment was conducted using Google's quantum processor to simulate wormhole dynamics through quantum entanglement. Consider this for a moment. The quantum entanglement Einstein despised might actually be the key to saving the spacetime described by his own general relativity. Could there be a twist more ironic, more beautiful than this? But here's where I want to draw an important line. What comes next is not scientifically established conclusion, but philosophical inquiry. If everything in the universe is in principle connected through quantum entanglement, is our consciousness also somehow connected to the entire cosmos? There's currently no empirical consensus that quantum entanglement directly connects to consciousness. This is not scientific fact, but philosophical question. Yet, even if there's a possibility of connection in principle, in our everyday macroscopic world, that connection becomes invisible through interaction with the environment. This is called decoherence. So let's organize what we've glimpsed from this exploration. Chapter 4. The World Revealed. Now, today we've explored quantum entanglement deeply. The strangest phenomenon in the universe, rejected by Einstein, proven by experiment. Can you see what this phenomenon is teaching us? Let's summarize the insights from today's exploration. First, Bell experiments proved that the framework of explaining reality with local hidden variables is difficult to maintain. Measurement results of distant particles are strongly correlated. While the correlation itself can appear independent of distance, in experiments loss and noise create distance constraints. The universe is far stranger than we thought. Second, at least in some interpretations, measurement is deeply connected to the determination of results. A particle's state is determined for the first time through the physical interaction called measurement. But the explanation of what is happening differs by interpretation. This suggests the nature of reality is not simple. Third, our intuition doesn't capture the essence of the cosmos. Even a genius like Einstein couldn't accept quantum strangeness. Yet the experiments are clear. The universe transcends our common sense. Quantum entanglement forces us to reconsider reality itself. At the boundary between science and philosophy, we face new questions. Understanding quantum entanglement changes how we see the universe. Stars don't simply exist in separation. At the quantum level, there's a possibility of correlation in some form. But in the macroscopic world, that connection becomes invisible. Science teaches us humility. The more we know, the more we realize our ignorance. Finally, I want to ask you, if the ER equals EPR conjecture is correct, quantum entanglement might be generating spacetime itself. So what is spacetime? And if quantum entanglement is the foundation of the universe, how should we understand the concept of separation? The answer to this question might birth the next revolution in physics. We continue our exploration. After you finish this video, when you return to everyday life, I want you to be just a bit more conscious. When you look up at the night sky, that the stars don't simply exist in separation, but hold the possibility of correlation through quantum history, and that science still holds many mysteries at the boundary between fact and interpretation. Quantum entanglement poses new questions to us. Not all answers have emerged. That's precisely why the exploration continues. Share your insights in the comments. Your questions become the force that propels this channel forward. Thank you for accompanying me on this intellectual journey to the end. Quantum entanglement is one of reality's deepest mysteries. On this channel, we continue exploring the cosmos, consciousness, and the essence of existence from both scientific and philosophical perspectives. If you seek intellectual adventures that shake established concepts, subscribe and continue this journey with us. Next time, too, an exploration awaits that will transform your worldview. Until next time.